Lambda calculus is a formal system in mathematical logic for expressing computation based on function abstraction and application using variable binding and substitution. It was first introduced by mathematician Alonzo Church in the 1930s as part of an investigation into the foundations of mathematics. Lambda calculus is a universal model of computation equivalent to a Turing machine. Its namesake, Greek letter lambda, is used in lambda terms to denote binding a variable in a function. Lambda calculus may be typed and untyped. In typed lambda calculus, functions can be applied only if they are capable of accepting the given input's type of data. Lambda calculus has applications in many different areas in mathematics, philosophy, linguistics, and computer science. Lambda calculus has played an important role in the development of the theory of programming languages. Functional programming languages implement the lambda calculus. Lambda calculus in history of mathematics. The lambda calculus was introduced by mathematician Alonzo Church in the 1930s as part of an investigation into the foundations of mathematics. The original system was shown to be logically inconsistent in 1935 when Stephen Kleene and J. B. Rosser developed the Kleene-Rosser paradox. Subsequently, in 1936, Church isolated and published just the portion relevant to computation, what is now called the untyped lambda calculus. In 1940, he also introduced a computationally weaker, but logically consistent system, known as the simply typed lambda calculus. Informal description. Motivation. Computable functions are a fundamental concept within computer science and mathematics. The lambda calculus provides a simple semantics for computation, enabling properties of computation to be studied formally. The lambda calculus incorporates two simplifications that make this semantics simple. The first simplification is that the lambda calculus treats functions anonymously, without giving them explicit names. For example, the function can be rewritten in anonymous form as similarly, can be rewritten in anonymous form as where the input is simply mapped to itself. The second simplification is that the lambda calculus only uses functions of a single input. An ordinary function that requires two inputs, for instance the function, can be reworked into an equivalent function that accepts a single input, and as output returns another function, that in turn accepts a single input. For example, can be reworked into this method, known as currying. Transforms a function that takes multiple arguments into a chain of functions each with a single argument. Function application of the function to the arguments yields at once, whereas evaluation of the curried version requires one more step to arrive at the same result. The lambda calculus consists of a language of lambda terms, which is defined by a certain formal syntax, and a set of transformation rules, which allow manipulation of the lambda terms. These transformation rules can be viewed as an equational theory or as an operational definition. As described above, all functions in the lambda calculus are anonymous functions, having no names. They only accept one input variable, with currying used to implement functions with several variables. Lambda terms. The syntax of the lambda calculus defines some expressions as valid lambda calculus expression and some as invalid, just as some strings of characters are valid C programs and some are not. A valid lambda calculus expression is called a lambda term. The following three rules give an inductive definition that can be applied to build all syntactically valid lambda terms. A variable is itself a valid lambda term. If is a lambda term, and is a variable, then is a lambda term. If and a lambda terms, then is a lambda term. Nothing else is a lambda term. Thus a lambda term is valid if and only if it can be obtained by repeated application of these three rules. However, some parentheses can be omitted according to certain rules. For example, the outermost parentheses are usually not written. See notation below. A lambda abstraction is a definition of an anonymous function that is capable of taking a single input and substituting it into the expression. It thus defines an anonymous function that takes and returns. For example, is a lambda abstraction for the function using the term for. The definition of a function with a lambda abstraction merely sets up the function but does not invoke it. The abstraction binds the variable in the term. An application represents the application of a function to an input, that is, it represents the act of calling function on input to produce. There is no concept in lambda calculus of variable declaration. In a definition such as, the lambda calculus treats as a variable that is not yet defined, the lambda abstraction is syntactically valid, and represents a function that adds its input to the yet unknown. Bracketing may be used and may be needed to disambiguate terms, for example, and denote different terms. Here the first example defines a function that defines a function and returns the result of applying x to the child function, while the second example defines a function that returns a function for any input and then returns it on application of x. Functions that operate on functions in lambda calculus. Functions are taken to be first-class values, so functions may be used as the inputs, or be returned as outputs from other functions. For example, represents the identity function, and represents the identity function applied to. Further, represents the constant function, the function that always returns, no matter the input. In lambda calculus, function application is regarded as left associative, so that means there are several notions of equivalence and reduction that allow lambda terms to be reduced to equivalent lambda terms. Alpha equivalence, a basic form of equivalence, definable on lambda terms, is alpha equivalence. It captures the intuition that the particular choice of a bound variable, in a lambda abstraction, does not matter. For instance, and are alpha equivalent lambda terms, and they both represent the same function. The terms are not alpha equivalent because they are not bound in a lambda abstraction. In many presentations, it is usual to identify alpha equivalent lambda terms. The following definitions are necessary in order to be able to define beta reduction. Free variables. The free variables of a term are those variables not bound by a lambda abstraction. The set of free variables of an expression is defined inductively. The free variables of a just. The set of free variables of is the set of free variables of but with removed. The set of free variables of is the union of the set of free variables of and the set of free variables of. For example, the lambda term representing the identity has no free variables, but the function has a single free variable. Capture avoiding substitutions. Suppose, and a lambda terms and n are variables. The notation indicates substitution of in a capture avoiding manner. This is defined so that, if n is not in the free variables of, the variable is said to be fresh. For example, and the freshness condition is crucial in order to ensure that substitution does not change the meaning of functions. For example, a substitution is made that ignores the freshness condition. This substitution turns the constant function into the identity by substitution. In general, failure to meet the freshness condition can be remedied by alpha renaming with a suitable fresh variable. For example, switching back to our correct notion of substitution, in the lambda abstraction can be renamed with a fresh variable, to obtain, and the meaning of the function is preserved by substitution. Beta reduction. The beta reduction rule states that an application of the form reduces to the term. The notation is used to indicate that beta reduces to, for example, for every. This demonstrates that really is the identity. Similarly, which demonstrates that is a constant function. The lambda calculus may be seen as an idealized functional programming language, like Haskell or standard ML. Under this view, beta reduction corresponds to a computational step. This step can be repeated by additional beta conversions until there are no more applications left to reduce. In the untyped lambda calculus, as presented here, this reduction process may not terminate. For instance, consider the term here, that is, the term reduces to itself in a single beta reduction, and therefore the reduction process will never terminate. Another aspect of the untyped lambda calculus is that it does not distinguish between different kinds of data. For instance, it may be desirable to write a function that only operates on numbers. However, in the untyped lambda calculus, there is no way to prevent a function from being applied to truth values, strings, or other non-number objects. Formal definition. Lambda expressions are composed of variables v1, v2, vn. The abstraction symbols lambda, and dot. Parentheses. The set of lambda expressions, lambda, can be defined inductively. If x is a variable, then x lambda. If x is a variable and m lambda, then lambda. If m, n lambda, then lambda. Instances of Rule 2 are known as abstractions and instances of Rule 3 are known as applications. Notation. To keep the notation of lambda expressions uncluttered, the following conventions are usually applied. Outermost parentheses are dropped. Mn instead of. Applications are assumed to be left associative. Mnp may be written instead of p. The body of an abstraction extends as far right as possible. Lambda x, Mn means lambda x, and not n. A sequence of abstractions is contracted. Lambda x, lambda y, lambda z, n is abbreviated as lambda x, y, z, n. Free and bound variables. The abstraction operator, lambda, is said to bind its variable wherever it occurs in the body of the abstraction. Variables that fall within the scope of an abstraction are said to be bound. All other variables are called free. For example, in the following expression, y is a bound variable and x is free. Lambda y, x, x, y. Also note that a variable is bound by its nearest abstraction. In the following example, the single occurrence of x in the expression is bound by the second lambda. Lambda x, y. The set of free variables of a lambda expression, m, is denoted as fv and is defined by recursion on the structure of the terms, as follows. Fv equals x, where x is a variable. Fv equals fe, x. Fv equals fv, fv. An expression that contains no free variables is said to be closed. Closed lambda expressions are also known as combinators and are equivalent to terms in combinatory logic. Reduction. The meaning of lambda expressions is defined by how expressions can be reduced. There are three kinds of reduction. Alpha conversion, changing bound variables. Beta reduction, applying functions to their arguments. Eta conversion, which captures a notion of extensionality. We also speak of the resulting equivalences. Two expressions are beta equivalent if they can be beta converted into the same expression, and alpha, eta equivalents are defined similarly. The term redex, short for reducible expression, refers to subterms that can be reduced by one of the reduction rules. For example, n is a beta redex in expressing the substitution of n for x in M. If x is not free in M, lambda x, mx is an eta redex. The expression to which a redex reduces is called its reduct, using the previous example. The reducts of these expressions are respectively m, x, equals n, and m. Alpha conversion, sometimes known as alpha renaming, allows bound variable names to be changed. For example, alpha conversion of lambda x, x might yield lambda y, y. Terms that differ only by alpha conversion are called alpha equivalent. Frequently, in uses of lambda calculus, alpha equivalent terms are considered to be equivalent. The precise rules for alpha conversion are not completely trivial. First, when alpha converting an abstraction, the only variable occurrences that are renamed are those that are bound to the same abstraction. For example, an alpha conversion of lambda x x could result in lambda y x, but it could not result in lambda y x, y. The latter has a different meaning from the original. Second, alpha conversion is not possible if it would result in a variable getting captured by a different abstraction. For example, if we replace x with y in lambda y x, we get lambda y y, which is not at all the same. In programming languages with static scope, alpha conversion can be used to make name resolution simpler by ensuring that no variable name masks a name in a containing scope. In the De Bruijn index notation, any two alpha equivalent terms are literally identical. Substitution, written E-V equals R, is the process of replacing all free occurrences of the variable V in the expression E with expression R. Substitution on terms of the lambda calculus is defined by recursion on the structure of terms, as follows. X equals n y x equals n y. If x y x equals n lambda x m x equals n lambda y. If x y, provided y f v to substitute into a lambda abstraction, it is sometimes necessary to alpha convert the expression. For example, it is not correct for y equals x to result in, because the substituted x was supposed to be free but ended up being bound. The correct substitution in this case is up to alpha equivalence. Notice that substitution is defined uniquely up to alpha equivalence. Beta reduction captures the idea of function application. Beta reduction is defined in terms of substitution. The beta reduction of E is E-V equals E. For example, assuming some encoding of 2, 7 times, we have the following beta reduction. 7 times 2. Eta conversion expresses the idea of extensionality, which in this context is that two functions are the same if and only if they give the same result for all arguments. Eta conversion converts between lambda x and f whenever x does not appear free in f, normal forms and confluence. For the untyped lambda calculus, beta reduction as a rewriting rule is neither strongly normalizing nor weakly normalizing. However, it can be shown that beta reduction is confluent. Therefore, both strongly normalizing terms and weakly normalizing terms have a unique normal form. For strongly normalizing terms, any reduction strategy is guaranteed to yield the normal form, whereas for weakly normalizing terms, some reduction strategies may fail to find it.